Recent scientific discussions suggest that time may not be the fundamental backbone of reality as we once believed. Instead, it could be an emergent phenomenon arising from the enigmatic realm of quantum mechanics. This revelation challenges our deepest intuitions and has profound implications for physics and our understanding of the universe. In this video, we will explore the meaning of this idea, the science behind it, and why it is so significant. Traditionally, time has been perceived as a constant, flowing uniformly from the past through the present and into the future. In classical physics, it serves as an absolute backdrop against which events unfold, independent of the observer or the events themselves. This perspective was famously articulated by Sir Isaac Newton, who described time as absolute, true, and mathematical, flowing uniformly regardless of external influences. This Newtonian view remained dominant until the early 20th century when Albert Einstein introduced his groundbreaking theories of relativity. In his special theory of relativity, Einstein proposed that time is not a universal constant but is instead relative, depending on the observer's motion. He demonstrated that as an object approaches the speed of light, time slows down for it relative to a stationary observer, a phenomenon known as time dilation. This was a radical shift from Newtonian mechanics, revealing that time is interwoven with space to form a four-dimensional continuum known as spacetime. Einstein's general theory of relativity further transformed our understanding by showing that gravity is not a force acting at a distance, as Newton had suggested, but rather a curvature of spacetime caused by mass and energy. In this framework, massive objects like planets and stars warp the fabric of spacetime, and this curvature dictates the motion of objects and the flow of time. For instance, time moves slightly faster on a mountaintop than at sea level due to the weaker gravitational field at higher altitudes. While this effect is subtle, it has been confirmed through precise atomic clock measurements. These relativistic effects are not just theoretical concepts but have practical consequences. GPS satellites orbiting Earth experience both reduced gravity and high velocities compared to an observer on the ground. According to Einstein's theories, lower gravity causes the satellite clocks to run faster, while their high speeds slow them down. The net result is that time on these satellites runs slightly faster than on Earth's surface. Without correction, this discrepancy would lead to navigational errors accumulating at a rate of approximately 10 kilometers per day. To maintain accuracy, GPS systems compensate for these relativistic time dilations, adjusting satellite clocks accordingly. Despite these revelations, both Newtonian mechanics and Einstein's relativity treat time as a fundamental dimension. Whether absolute or relative, time is still considered an intrinsic part of the universe's fabric. In quantum mechanics, however, time is often treated as an external parameter, a fixed backdrop against which the probabilities of different outcomes evolve. This stands in contrast to the relativistic view, where time is intertwined with space and influenced by gravity. One of the most intriguing aspects of quantum mechanics is entanglement, where particles become so deeply connected that the state of one instantaneously affects the state of another, regardless of the distance between them. This spooky action at a distance, as Einstein described it, has been experimentally confirmed and suggests that information can be correlated across vast distances without any time delay. Such instantaneous connections challenge the classical notion of causality, which relies on a temporal sequence of cause and effect. Recent studies suggest that time itself may emerge from quantum entanglement. The Page and Wouters mechanism, proposed in 1983, suggests that time arises from correlations within an entangled system. In this framework, one part of the system can act as a clock, and its entanglement with another part gives rise to the perception of time passing. Without such entanglement, the universe would appear static and unchanging, implying that time is not a fundamental entity but rather a byproduct of quantum correlations. This idea aligns with the Wheeler-DeWitt equation in quantum gravity, which intriguingly omits time altogether. This equation describes the quantum state of the entire universe, implying a timeless wave function. According to this perspective, time emerges only when considering subsystems in relation to one another, reinforcing the idea that time is not a fundamental background but an emergent property resulting from quantum interactions and entanglement. The concept of emergent time challenges traditional distinctions between space and time in relativity and the fixed parameter of time in quantum mechanics. suggests that the idea that time emerges from more fundamental quantum processes could provide a groundbreaking resolution to the long-standing conflicts between the two pillars of modern physics, quantum mechanics and general relativity. By offering a unified understanding of the cosmos, this perspective may pave the way for revolutionary advancements in physics. Viewing time as an emergent phenomenon also opens exciting possibilities in fields like quantum computing and information theory. If time arises from quantum correlations, then manipulating these correlations could introduce novel methods of processing information, potentially transforming modern technology. This notion challenges deeply ingrained beliefs about reality, causality, and consciousness. Traditionally, we perceive reality as a sequence of events unfolding from the past, through the present, and into the future. However, if time is a product of quantum correlations, then reality might resemble a static block where all moments coexist simultaneously. Our perception of now could simply be a construct of our minds. This perspective aligns with Einstein's theory of relativity, which suggests that all points in spacetime are equally real, undermining the idea of a universal present. If true, reality may not be as dynamic as it feels, but instead a subjective experience shaped by human perception and interaction with the universe. The concept of emergent time could also revolutionize efforts to unify quantum mechanics and general relativity, two of the most successful yet seemingly incompatible theories. General relativity treats time as a dynamic entity influenced by gravity, while quantum mechanics treats it as an external parameter. Emerging theories such as string theory and loop quantum gravity suggest that spacetime, and by extension time itself, may not be fundamental but instead arise from deeper quantum structures. For instance, string theory proposes that time may emerge from the vibrational patterns of fundamental strings, seamlessly blending with the fabric of spacetime. Similarly, loop quantum gravity suggests that spacetime consists of discrete units, with time emerging from their interactions. Meanwhile, the Wheeler-DeWitt equation describes the universe in a timeless state, with time appearing only when considering subsystems relative to one another. These ideas represent a paradigm shift in physics, where time ceases to be a fundamental variable and instead emerges from a deeper, unified framework. The emergent nature of time also raises profound questions about human consciousness. Some theories suggest that our brains impose a sense of flow and causality onto a timeless quantum reality. Neuroscientific research reveals that the brain organizes sensory inputs to construct a coherent narrative of past, present, and future, an ability essential for survival, allowing us to anticipate dangers and plan ahead. But if time is merely an illusion, what does this mean for concepts like free will and causality? Could our perception of time be a survival mechanism rather than a reflection of objective reality? The implications of emergent time extend beyond physics into philosophy and everyday life. Philosophically, it challenges the notion of free will. If all moments in time coexist, as suggested by the block universe model, then our choices may be predetermined, with a feeling of freedom merely an illusion. Thank you for watching. We hope you enjoyed this exploration of time as an emergent phenomenon. If you found this discussion insightful, don't forget to like, subscribe, and share.